Okay, so it's my great pleasure to introduce Roberto La Scala, who will talk about ciphers and difference equations today. Thank you, Roberto. Please.
So let me thank you for this possibility to speak to your important, interesting seminar. What I want to discuss today is this relationship between system of difference equation and cipher cryptography. As a matter of fact, there are many important cipher which are actually used in application, which are related, which are defined in terms of different system over finite field. They are essentially recursive rules which defines the evolution over the time of some discrete time of a vector, which is usually called the state, the register of the cipher, with entries in a finite field. The recursion is defined by means of some state transition function, which is a polynomial one, and which is generally the one which corresponds to a system of explicit ordinary difference equation. Just to show that this is something which is already there, I will provide a couple of examples that will guide us in this formalization of the notion of different cipher. For instance, Trivium is a cipher which was developed in Europe, in Belgium exactly, within the project eStream. It is one of 3 winners for a call for hardware efficient stream cipher. Trivium was published in 2003. It is quite simple, as you will see, as a system of difference equation, but no attack, in fact, have been made to this cipher that really make it unusable. So it is still there, still safe. These are the state equation that defines the evolution of the internal state of the cipher in some standard notation in difference algebra. In fact, I will use some a little bit more compact notation of this kind. I will avoid the use of these powers of sigma. The coefficient of the system are in the constant finite field, the field with 2 elements. And we are interested in solution in sequences of this system of difference equations. So there are, function from the natural numbers into the field with 2 elements. We are interested in such solution. Since it is an explicit difference a system of explicit difference equation, we have one-to-one correspondence between solution and their initial states. The evolution of the system corresponds to the initial states of the solution. And we can denote by V0 this initial state. For each clock t, the state evolves during the time, and the state is a vector of the space zeta 2 to the power 288, because 93, 84, and 111 is the order of the equation in the system. The state transition function, so it's this polynomial map, vector polynomial map, which sends the state at clock t into the states at clock t plus 1. The key and the initial vector of this cipher, the initial vector is some kind of additional key, are 80 plus 80, 160 bit of the initial state, and the remaining 128 are fixed. But essentially the key for this cipher is the initial state of the different system. Together with this nonlinear difference system, which determines the evolution of the internal state of this cipher, Trivium, we have a polynomial, so-called the key stream polynomial, which defines the output of the cipher. The output of the cipher is the evaluation of this polynomial over the internal state. These are single bit, this determines a pseudo-random bit stream, which is the output of the cipher. This is a stream cipher. So the output of the cipher is a sequence of pseudo-random bits. In fact, the key stream outputs for a large clock T. It's the key stream outputs after some number of clocks at some point. No, and this is done in order to protect the initial state, which contains the key. So this key stream, in fact, appears from the clock 1152 for the case of Trivium. And this is made for, security issue. In cryptanalysis, since Trivium is very hard to attack, there is some variant, which is just a couple of its equation. We consider a couple of equations. And the key stream polynomial is this one. Here, the vector is 177 bit, the state has such length, and the key streams outputs after 708 clocks at some point, 4 times the length of the register as for Trivium. Note that the state transition function, both of Bivium and Trivium, are invertible maps. This means that one can compute the initial state starting with any state. You can reverse the time in this system. This is a potential weakness because this means that it's possible to attack any internal state instead of the initial state because the system is invertible. On the other hand, the property of a system to be invertible and at the same time contain some subsystem is reducible can be considered a resource, because in this way you can define a symmetric block cipher from a different system of equation, explicit equation over a finite field, instead of defining a stream cipher. So if you have some invertible system, which is also reducible, you can define a symmetric block cipher. An invertible system containing a subsystem defines a symmetric block cipher. The initial state of the subsystem is the key of the cipher. The initial state of the system is the pair of the key with the plain text. For a fixed clock T, if you consider the state at this final clock T, this part corresponds to the plain text becomes the ciphertext. So after some number of cycles, you have the encoding, you have the ciphertext starting from the plain text. So to decrypt using the key subsystem, you can compute UT starting with the initial key, which is U0, the initial state of the subsystem. So the inverse system is then able to compute the initial state E0, V0, and hence the plain text V0, starting with the final state using the fact that the system is invertible. So you have a very simple way to define also a symmetric block cipher. And an example of this is this cipher, keylock, which is used for radio frequencies transponder for car immobilizer, door opening, this kind of application. It's a small block size cipher. The patent of keylock was sold in 1995 for 10 million US dollar, but in fact, mathematicians have been cryptanalyzed it in some critical way in 2008. And these are the equations. It's a system of 2 equations where the subsystem is simple this linear equation, which is a rotation over the key. And this is the other equation which produce by means of the key and the initial state of this variable and the many state of the variable x defines the evolution of the plain text towards the ciphertext. So the key subsystem is this single linear equation. The state of the system is the length of the key 64 plus 32, which is the length of the I mean the block. And the state of the key subsystem is some, of course, vector of zeta2 to power 64. The final clock of this cipher is 528. So the key are the initial state of the variable k. The plain text is the initial, this part of the initial state of the system relative to the variable x, and the ciphertext is v at time 528. And the critical weakness for keylocks was the small period 64 of the key subsystem, which allowed some attack. So formalization for all of this. Formalization is, I mean, difference algebra, because we are dealing with system of this different equation over some field. For us, it's a finite field, but let's consider some generic field. So I will, I mean, recall some basic notion here. Most likely, I mean, the notation will be a little bit different, but after all, we have some finite sets of variables for each clock t, for each integer t. We form the variable set as the joint of all these finite set, and we consider the algebra endomorphism sigma from this polynomial ring R, which is the polynomial algebra over this infinite number of variables. And this sigma maps some variables at time t into the corresponding variables time t plus 1. It's called shift map. So the algebra R endowed with the map sigma is called, you know very well, the algebra of ordinary difference polynomial in the variable x1, xn. Consider now some integer, which will be the order of our equation. We need also some subset of variables, which are the initial variables, and we x bar, and we will consider the corresponding subalgebra as the polynomial algebra over this subset of initial variables. So generally, an explicit system of explicit ordinary difference equation will be defined by means of some polynomials f1, fn belonging to R bar, and it is such system. A K solution in sequence of the system is an n-tuple A1, AN, where AI are sequence and satisfy this equation, of course. For each system, we define a corresponding algebra endomorphism. Let's call it T bar from R bar into R bar, which is the endomorphism which send each variable at some time as each initial variables into the corresponding variables at time t plus 1. So we have this endomorphism. If we define R as the sum of this Ri, we denote by T the corresponding polynomial function, which corresponds to this endomorphism. So for each T, we have that this polynomial function determine the evolution of the states. So it maps Vt into Vt plus 1 for any solution. And we call T bar the state transition endomorphism and T the state transition map of the system 1. We will denote by V of K the set of all K solution of the system, and we have, of course, a bijective map which maps the solution into their initial states, and this map is bijective and polynomial 1. Now we have this, it is important to know if the system is invertible or not, so we have this definition, the endomorphism T bar corresponding to some system. So the system is called invertible if the state transition endomorphism is an automorphism. In this case, the corresponding polynomial map is also a bijective map. The Grebener basis, so it's important to us to know if the system is invertible or not. That Grebener basis provides an algorithmic method to determine if an endomorphism between on a polynomial algebra is invertible or not, and to compute its inverse. So let me recall this method. If you have some finite set of variables, consider some endomorphism phi you consider the polynomial algebra over this finite set of variables and consider some endomorphism phi from P into P. We take some copy of this finite set X prime, and we consider some copy of the polynomial algebra P, let's call it P prime, and consider Q, which is the polynomial algebra over the join of these two sets, tensor product of these two polynomials. And so we consider, given this endomorphism phi, we consider a corresponding ideal J, which is generated by this equation corresponding to, the definition of the map, where we use this extra variable X prime. And we endowed this polynomial algebra, a product monomial order, where the variable X are greater than the variable X prime. Then phi is an automorphism of P if and only if the reduced Gröbner basis of J is of this kind. This kind of Gröbner basis gives immediately the definition of the inverse phi minus 1, which is given in this way. So we have some well-known symbolic methods to know if an endomorphism is invertible to compute its inverse. If we apply this to our system of explicit equation, difference equation, we will apply this theorem for state transition endomorphism. So if T bar is the state transition automorphism corresponding to an invertible system, if we compute the Gröbner basis of the ideal corresponding to the definition of T bar, the Gröbner basis is of this kind. And this immediately gives the definition of the inverse system of our explicit difference system, but note that we have to reverse the order of the variables to have exactly, the state transition endomorphism. The corresponding map is the state transition endomorphism of some different system. So up to this trick, you consider this, isomorphism of R bar prime into R bar, which reverse the variables and deletes this prime. The inverse system, you go under this isomorphism and you transform this F prime I that you obtain the Gröbner basis here into the polynomial GI. So the inverse system of an invertible system is by definition such a system of difference equation. Now, of course, the state transition endomorphism and the corresponding state transition maps on invertible system and its inverse system are one the inverse of the other, up to the following permutation, which reverse the variable. So this allows to compute the initial state starting with any state of our system 1 by consider Vt as the initial state of the inverse system. So by means of the inverse system, we can reverse the time over our system of difference equation. For instance, for trivium, we have the system defining the evolution of the internal state of this Cipher trivium. By means of this symbolic computation technique, we can compute the inverse of this system, which is this one. And this will be useful for the cryptanalysis of this cipher because it allows to attack some internal state instead of the initial state, which represent the key. Another couple of useful notions are the following. A system is reducible if it contains some subset of equation which depends only on a subset of variables. In this case, the state transition endomorphism and map are just the restriction. So we have some independent subsystem inside the system. And also, if T is the state transition map on an invertible system, we will call the system periodic if there is some finite period for the map T, for the state transition map. In this case, the solution are a periodic function. And note that if we have a finite field, all invertible systems are periodic. So one problem, up to my knowledge, is to evaluate the period of some polynomial map, which is nonlinear one, and to maximize such possibly some period. This is can be done easily for linear difference equation, but what about nonlinear system of equations, so nonlinear polynomial maps? This would be important for, security of a system, because we noted that for a block cipher made out of a system of difference equation which contains a subsystem, key subsystem, the period of the key subsystem should be long to provide security. Otherwise, it's weak. So let we define now different cipher. Consider that our base field is a finite field. A different stream cipher, for instance, is by definition an explicit different system together with a polynomial. If A1 and An is a K solution in sequence of the system, its initial state, we can call it the key of this solution. And if Vt denotes a state, a generic state at time t of this solution, the function B, which is called the key stream, the output of this solution, is simply defined as the value that the polynomial f has over this internal state Vt for all t greater than, for all time, for all clocks. And we call f the key stream polynomial of C. So the output of the cipher is this function. Note that such a cipher can be considered some explicit system of some special kind, because this, this key stream is just the solution for some additional variable y. So we can consider a different stream cipher just as a system of explicit difference equation over finite field. Now the problem is, what does it mean to provide an algebraic attack to such a cipher? No, what we know from the cipher is its output. We know its output from some clock on. So we have the value, we know some amount of values of this key stream, this sequence of bits or element from the finite field that outputs this, this system by means of its evolution and by means of the evaluation of this polynomial over the internal state. So given C, a stream cipher defined by a system 1 and by a polynomial f, assume that B is the key stream of some K solution of the system and fix a clock T. Consider the ideal J, which is defined by this polynomial, which corresponds to the fact that we have some given evaluation of the polynomial f over some sequence of values. So we are providing some, some amount of the key stream starting with the clock capital T. So we can denote by Vk of J the set of the solution. So an algebraic attack to the cipher by given the key stream B after T clocks is the computation of the solution of the system, such that such solution belongs to this variety, satisfy this equation. In other words, we considered, if you consider the difference ideal corresponding to the system, you want to compute the solution for the sum of the ideal I corresponding to the system plus J. You are imposing some condition to the solution. Note that for the difference algebra are with coefficient the constant field K, which is the most natural assumption for describing this system of difference equation, which corresponds to, to cipher, the ideal J is not a difference one. It's not a difference ideal. So we escape from the context of difference ideal, because I is a different ideal, but J is not such. And we want to compute this, the solution, the variety of the K solution of the system that are compatible with the given key stream. We provide the key stream and we want to know what are the solutions of the system. We are especially interested in the initial state of such solution, which are compatible with the given key stream, because at the key of the cipher, which provides such key stream. And these keys are the goal for such an attack. So we want to know which key would provide, may provide this given key stream that we observe. No, this is exactly what cryptanalysis do. Want to understand the key given some information about the cipher. For us, for a stream cipher, it's the key stream. We know some amount of bit of the key stream. I want to know the initial state, the initial states. So it may be convenient to compute directly the equation for the variety of the compatible keys. So we want the equation for the initial condition instead of the equation for all the solution. Of course, this is the image of the variety of the solution under this polynomial bijection, which maps a solution over its initial state. And we can compute, we can compute the equation of such initial state. For instance, if you assume that you have a monomial ordering of the algebra of difference polynomial, which is compatible with the shift map such that, the term xi as greater than the leading monomial, all the other, monomial that appears on the right-hand side of the equation, you have that the set corresponding to the equation of the system is a difference Gröbner basis, which means that up to shift all, you have a Gröbner basis. And by defining f prime t as the normal form of the polynomial sigma t of f modulo I with respect to such difference equation, the ideal J prime, and you define the ideal J prime by means as, the ideal generated by this normal form minus bt, which is the elements in the key stream. You have that exactly this variety, these sets of key which are compatible with the given key stream have such equation, satisfy such equation. So what we have done essentially is to eliminate all variables from the system except for the initial one. So in this way, we get the equation for the initial states. And we are interested mainly in this. Note the following, that in a practical algebraic attack, we don't know all the values of the key stream of these special variables starting from the clock t, but some amount, finite amount of them. So in fact, we have this ideal, which is finitely generated. But of course, since, this J prime is the union of this ideal, so we have an ascending chain, and the algebra over the initial variables is a finitely generated, so an Euclidean. We have that J prime B is equal to J prime for some suitable large value B. In other words, for a sufficient number of key stream values, we don't lose any equation satisfied by the key. So if we allow some, enough number of values for these special variables, which is the key stream, we don't lose any equation. We will get exactly the key that we have really. So for compute, so the problem now is to compute this. We have a system of equation over a polynomial algebra in a finite number of variables, which are the initial variables for the system, and we want to compute, the solution over the field K, which is a finite finite field, and we can use many things as solver. We can use Gröbner basis or South solver because satisfiability of satisfiability problem of Boolean equation corresponds to solving polynomial equation over the field with two elements. We can use characteristic set, triangular set, other solvers. And note also this, that for actual cipher, if you consider Trivium, other ciphers, what you have is that generally there is a single key which is compatible with the given key stream. So you can search for a single solution. If you search for a single solution, which is the general situation in practice, you can apply, for instance, the Nullstellensatz for finite field. You have this proposition, this known proposition, that if you have the polynomial algebra over a finite field and you consider the ideal corresponding to the equation of the field, if J is any ideal, and you consider the set of solution of an algebraic closure of the field K, you have that the solution of the field equation is the affine space over the coefficient field. And if you look for the solution inside the coefficient field, you have just to consider the solution in the algebraic closure of the sum of the ideal with the field equation, the finite field equation you are considering. And J plus L is a radical ideal. So by the Nullstellensatz, if you assume that the variety consists of a single element, you have that the Gröber basis of the ideal J plus L is of this kind, gives immediately the solution of this system. And it's important to note that it is a universal Gröber basis. It's a Gröber basis with respect, since it is linear, it's universal. It's a Gröber basis with respect to any monomial ordering you consider for P. Because to solve a system, you will need probably some lexicographic ordering or to change ordering by this method, FGLM, this kind of things. But if you search for a single solution, you perform some single Gröber basis, you get the solution. So the above result is very useful for algebraic attacks because Gröber bases are very sensitive on monomial orderings. And in the case of a single solution, you can choose the most efficient monomial orderings, which will be probably Degrevlex, some monomial ordering, which is based on the degree. Another possible optimization, since you know that the Gröber basis is of this kind, you can stop your computation when you get that all variables appears in the current Gröber basis. This, I mean, allows some, you save some amount of time in doing this, but okay, this is a minor optimization. But a main optimization is the following. Note that the normal form f prime t, the normal form which is obtained by eliminating all variables except for the initial one from the polynomial sigma t to the f, have general high degrees because the initial clock t, which is chosen for the real cipher, is large. So you have to eliminate a lot of shift. So the degree of this normal form is generally high. So that's a problem because you have a system of equation of high degree to solve. But if the system is invertible, you can essentially assume that the key streams start at clock 0 because you can reverse the time. So by using the inverse system, you can attack any state instead of the initial state. And this is very important optimization because it reduces drastically the degree of the generator of the ideal you have to solve. Because you, instead of considering this with t that goes to b, you consider this g double prime b, where t goes to b minus t. B minus t is exactly the number of the key stream bit, the key stream element you are providing. So this reduces the degree of the equation you have to solve. And we have used in practice this strategy to attack this stream cipher devium. But in some cases, the normal form still have 2 high degrees, even if you consider this trick. No way. You have to, an alternative strategy is to compute the solution instead of their initial state. Because for solution, the condition you are imposing is of this kind, sigma t f minus bt. But all polynomials sigma t f have all the same degree. So you have not increased the degree. But the problem with this, the drawback is that Grover basis computation requires solving of a large number of variables, because are the initial variables which are shift till some points. So a large number of variables. But if you can do anything else, you have to stay in this setting. When you compute a Grover basis to obtain the solution of a system, a fundamental strategy is to have linear polynomial, because I mean, for this real world system to solve with a single Grover basis, this equation is too much. So there's some standard strategies to impose some linear polynomials. These linear polynomials can be given or computing inside the ideal J, or they may correspond to some, I mean, random evaluation of some subset of variables. So you evaluate some subset of variable in some exhaustive way. So you impose some linear equation, and this, of course, reduces the complexity of the Grover basis of the solver that you have to perform. So if some of this evaluation is wrong, since you have one single solution in your system, you get no solution. So you get an ideal which have no solution. For the, I mean, symbolic computation, for symbolic computation, this is not a bad situation, because the Grover basis stops once some constant is obtained. And note that instead, for such solver, the answer unsat, that the system of Boolean equation cannot be satisfied, arrives when you have more or less considered all the entire space. So for such solver, the no solution is worse than solution. But for symbolic computation, somehow it is better. And note that you are, I mean, evaluating a subset of variables in all possible way, an exhaustive way. So this means that all the evaluation except that one are without solution, have no solution. So all systems you are considered except and one have no solution, are inconsistent. So even in practice, you know, the Grover basis performs better than such solver. Why I consider such solver? Because such solver have some good reputation in cryptography. But in practice, we notice that under this kind of strategies, Grover basis perform much better. Solving an algebraic system by means of the complete evaluation of a subset of variables is called a guess and determine, or hybrid, because it's a mix of brute force with solving, hybrid strategy, or guess and determine strategy. Of course, the practical complexity is Q to the S, since Q is the, I mean, the cardinality, the number of elements of the finite field, to S, where S is the number of variables to be evaluated, times the average computing time for a single Grover basis. Then you can reduce to Q to the S over 2 if you consider with probability greater than 1/2 that the solution is in half of the space, but this is some minor consideration. So, I mean, you, instead of computing one single Grover basis that cannot be computed, you trade off with some amount of Grover basis that can be computed. The problem is how big is this power Q to the S. So a fundamental optimization consists of the choice of variables that you have to evaluate. And the parallelization, since you have to perform all this computation, you can go parallel if you can. Or you divide the guess space into pieces and go in a parallel way. Okay, these are some, I mean, technical issues. So for our algebraic, we provide some example. an algebraic attack to Bivium, we evaluated 38 variables and using some linear equation because the key string polynomial is linear. So you can use this linear equation, which belongs to your ideal. You obtain for 38 the evaluation of 60 variables out of a total of 177, which is the length of the state of the register, which means that you solve 117 variables. So you evaluate 38, but solve 117 variables, and you can do this in 10th of seconds. So for Grabner basis, in our experience, we have used a couple of implementation of Buperian algorithm that you can find this open source system, free open source singular. And we have compared Grabner basis with a couple of SAT solvers which are widely used in cryptography. They are called Minisat and Crypro-Minisat. The running time of our attack is 2 to power 34, which is much less than the length of the key, which is 80, or if you consider the couple of variables of key is 80 plus 80. So it's much better than brute force. That's the point. And the attack can be even parallelized. And this is, I mean, some timing we have obtained. And you note that for wrong evaluation, which are all except then one, you obtain 364 milliseconds, so 10th of seconds against 20 seconds with respect to the better SAT solver when solving. So Grabner basis performs much better than SAT solver, and you can solve a system with 100 variables in such a small time. So this is something that you can do really. So we recall to end, I mean, to conclude my talk, I just want to give some idea about block ciphers. For block cipher, you need some
Roberto,
reducing.
may I interrupt you?
Yes.
So we're a little bit out of schedule. So maybe we can like once you have described the attack, we have defeated Bivium, maybe we can stop for a break and continue after the break. Would this sound good to you?
As you want. I have few slides to show just some conclusion. It's up to you.
Okay, then maybe let's talk about this after the break, so that we will comprehend the prior slides of the break, and we'll be more ready for the conclusion. So Ronnie will arrange the rooms now.
It's okay.
Okay, good. Well, welcome back, everyone. So, and we will continue with the second part of the Roberto's talk.
Okay, I just want to conclude. I want to give you some idea about what is a block cipher made out of. I have already given you this idea by using this key lock system, but let's see in the informal way. We have a difference block cipher is defined by an invertible and reducible system together with some integer capital T. If 4 is the subsystem of our system 1, we put K, the sum of the order of the subsystem, and A, the sum of the order of the remaining equation. If UT-VT is the state at clock T of a solution of the system, we call the first part of the initial state the key. V0 is the plaintext, and V at final time is the ciphertext of the cipher. And we call for the key subsystem of the cipher. So the encryption is the map V0 into VT. So we perform this evolution, and at the end, in this second part, we obtain the ciphertext. If 2 is the inverse system of our system, and 4 is the key subsystem of our system 1, if U0 is the key of some solution, we can compute U of T by means of the subsystem without knowing V0, because we have this subsystem. And so for the part U, starting from the initial state, we can arrive to the final state. But once we have the final state for U, together with the plain text VT, by means of the inverse system, we are able to compute the initial state U0, V0, where V0 is the plain text. This provides decoding. Decryption function is obtained this way. What does it mean to attack a difference block cipher? This means to impose that we know some pair of plain text and ciphertext. This is called in cryptography known plain text attack. We know some amount of pairs, which are some condition that you are imposing, some equation that you are imposing. At time 0, plain text. At time t, ciphertext. So you are imposing some amount of linear equation, and you want to solve for solution of the system. You want the solution of the system which satisfies such condition, some linear condition. So if you, I mean, denote by J this initial and final condition for some amount of plain text ciphertext pair, you want to compute the solution of this, the solution of the system compatible with this condition. We overlook many variants of attack for this. We can use multiple plain text ciphertext pairs in order to provide enough condition to have a single key compatible with this. And one weakness for such kind of ciphers is to have some key subsystem or small period. And this happens, for instance, for key lock, where the key subsystem consists of this single linear equation, and which is a single linear one. And I mean, cryptography linear difference equations are called LFSR, linear feedback shift register. This was the first cipher that people used for system of linear difference equation somehow. In this case, the subsystem is a single LFSR, single linear difference equation of period 64. So it's too small, and this allows some attack. So let me draw briefly some conclusion. System of explicit difference equation over finite field model mainstream and block ciphers or application interest. It's not, I mean, an exercise. There exists a real cipher that are defined in terms of difference equation. For instance, in your Bluetooth stuff, you have some stream cipher which is called E0, and this E0 is a system of difference equation. This modeling allows to study this idea to model in terms of difference equation, which is very natural from a mathematical viewpoint, allows to study important properties of the cipher, such as their invertibility, and to define in some correct way what is an algebraic attack. Algebraic attacks are not the only one. There are other kinds of attacks, but for algebraic attack, which means to solve a system of equation, polynomial equation, the appropriate way is via this formalization in terms of difference algebra and so on. So the notion of different cipher allows to develop new cipher. To develop new cipher, you have just to introduce different system of explicit equation over finite fields, and to study, of course, their cryptanalysis, how difficult it is to provide some attack, given some condition to obtain the initial state, and so and so. But these two tools are essential in cryptography, because you can develop new idea for ciphers, and you have some method to control that these ciphers are secure or not, because of course the value of a cipher is its security that comes through cryptanalysis, evaluation, how difficult it is to provide an attack to such things. All details on what I have discussed today can be found in this paper, which is up to now in this archive. And okay, if I can suggest some further direction for research, I can mention this, for instance, to develop some symbolic method to compute and maximize the period of an invertible system in the nonlinear case, because up to my knowledge, I have no idea how to, to evaluate the period of such polynomial maps. But of course, to have large period for such map, for such, system of large period, which are periodic with a large period, it's important for security. Another possibility is to extend this transition map to more general endomorphism, more general function, and this will include in the same theoretical method more ciphers. So we have some model, theoretical model, and inside this we find a lot of known and useful cipher. One direction is to study the problem of preserving the difference ideal structure when one evaluates a variable over the sequence of its values. This corresponds to the problem of imposing a given key stream on a different stream cipher. Because as I mentioned, when I impose this condition, I lose this different structure, which is bad because at the beginning, I would like to have some difference Grober basis instead of Grober basis as a method to solve. But I cannot do this because this condition that I'm imposing are not a difference kind, so are not shift invariants up to now. And of course, to develop and implement efficient solvers like difference Grober basis, characteristic set, which are available to find solution for different system under such condition. This would improve the efficiency of this attack, so it would improve the cryptanalysis of this. If we can improve the complexity, reduce the complexity of providing an attack, this is very interesting because it improves the knowledge that we have of the security of such system. And since, we are dealing with system of equations that are invariant under some map, we would like to use this information to improve our solving technique. In general, this would sound some kind of call to arms for your community to make use of all powerful notions and methods of formal theory of ordinary difference equation to develop and analyze cipher. To solve polynomial equations is it's not the only way. There are many techniques in this nice world of ordinary difference equation that can be used. And it will be extremely interesting to see if these tools, these methods, this theory can be used in the context of system of explicit difference equation over finite fields. So we have this problem that here the meaningful coefficient fields are finite one, but this should be not, some obstacle. We should, I would like to try some methods for the formal theory of difference equation in this context. And this, I can, guarantee that this would be of great interest because, of course, cryptography is an interesting field, and any new viewpoint about this would be highly appreciated. So I stop here. Thank you for your attention.
Thank you very much, Roberto. Questions to the speaker, please. Just unmute yourself and ask. Or there's a question in the chat. Oh, Roberto, do you see the chat? Alexei Ovchinnikov is asking about slide 10, about numbers. So the question is about slide
chat. Okay,
10.
Okay, I see. I-64, but I think it's on slide. Where do 8 and 16 comes from? This is some, design of the cipher. No, they perform 8 times. As for trivium, I mean, the number of the clock where something starts or ends in some is some multiple of the length of some register. This 64 is the length of the key, is the length of the key. So they perform eight rotation of the key plus some amount, some extra amount, which is this 16. This 16 is an extra amount because to go to a multiple of the period of the key may be dangerous, for some kind of attack, because this map, this map which represents, which provides the evolution of the key is some powers, is the 8th power of a rotation. So this is the meaning of 8 times 64. 64 is the length of the key. So 8 times the length of the key plus some extra amount of rotation.
Okay, thank you. Other questions? Okay, some again the chat. Oh, there are 2 questions.
To add the linear equation. And I mean, for instance, there in this bivium example, we have that key stream is a linear equation, bivium, trivium. The key stream polynomial is a linear equation. So this linear equation belongs to the system that you want to solve. So these linear equations are already there inside the ideal. And you can use, what we have done is to perform some Gauss elimination over this linear equation in order to get, how to call, free variables, pivot variables in terms of free variables. So we provide the evaluation of some 30 variables, and by means of the linear equation, we get the evaluation of 60 variables. So we optimize, we reduce the number of variables that we want to evaluate. Besides of this, if you don't have, any other, linear equation inside your system, you can guess a linear equation, no? You guess. You say, okay, for some subset of variables, assume that the value of this variable is such. You guess for them. And of course, this reduces the complexity of solving the system to the price that you have to evaluate in some exhaustive way all these subsets of variables. So instead of computing a single Cryptography basis, you have to compute many. But the single one you cannot compute anyway. So it's better to compute many, at least from my viewpoint, better to compute many that you can really compute instead of a single one that you can never compute. So this is something that people do when solving a system of linear equation over finite field. They evaluate in some exhaustive way. This is some, it's some trade-off of brute force with solving. Because Cryptography basis solves well for some kind of system. You cannot predict, forecast which system will be solved well or bad, usually. Okay, regular sequence are solved well, but how to know that some sets of polynomials is a regular sequence? By means of Cryptography basis, you cannot do this, otherwise you have already solved your problem. In some cases, people assume that they have some regular sequences because the polynomial are random ones inside some large number of variables, and this provides a minimal, complexity for Cryptography basis provided by F4, F5 algorithms from Fourier, so and so. But generally, you cannot know this in advance. So people just try. So another, would different cipher be useful in a password protect situation. I mean, I think yes, in the sense that the cipher are usually used for to encode password, because when we enter some password somewhere, usually this password, I mean, is transmitted along internet in some encrypted way. So to have that your password is protected when it's transmitted along internet, it should be encrypted. And there are many ways to encrypt, but I mean, one way is to use block cipher, to use, I don't know, public key, private key, all, I mean, the standard means of cryptography. But of course, one way is to use system of difference equation over finite fields. So you have some plain text, which is the initial state. At the final state, you have the encryption in your password. Your password is the initial state of the system. After some amount of this evolution, you get some different things, which is the encryption of your password, if I understand correctly what you asked for.
But in the password protect system, the problem is not to recover your initial password, but rather to put in some other key that actually matches whatever encrypted password is stored in the system. In other words, if your ciphertext at the final stage of your algorithm is stored instead of the initial password, which is the usual case, right? People say that, well, we don't store your password, but somehow you store an encrypted version of your password.
Yes.
Now, then in a periodic system, then I could use a random keyword to continue your cipher algorithm, your encryption algorithm, and eventually I will get to your ciphertext, right? Because it's periodic. So that means that I would be able to put in something, and then your system, when you check whether it agrees with the ciphertext protected, which is the protected encrypted password, it will match it. And so therefore it's not secure at all. In fact, the longer the period, the easier it is to use a random initial key phrase to get to your cipher text to match it, right? Because it's periodic.
Yes, I mean, there are a lot of tricks that are used, I mean, in cryptography to avoid this kind of problems. For instance, they try this key string polynomial, for instance, is some, I mean, amount of information from the state. So what goes out of the system is some partial information, not the full, of course, not full information about the state. So you extract some bits from the state, and this is what goes in output. So from this reduced number of information, it's very difficult to, I mean, to obtain the real state and go up and down by means of the periodic structure or invertibility structure of the system.
Okay.
Okay, so there is one more question in the chat about using singular versus perhaps other possible kernel-based software.
You mean I've used? You mean me?
Yes.
Of course, we know that don't know, Magma is a very good system, but I mean we have a lot of experience with Singular. That's the main point. So we know how to do all things, and Singular is I mean it's a very serious system. And I mean, even if we would use, don't know, magma instead of singular. When we have 10th of seconds, it will change a little bit. It's a constant in our complexity. Main complexity is the number of variables that you have to evaluate, the number of guesses. This is the real complexity. Up to a constant, the constants may be the average solving time. Will change, I mean, few. If your solving times is 1 second or less on 10th of seconds, this will not change really the complexity. So we prefer to do this way, even to compare with other, I mean, papers in literature where people use singular. But I mean, my experience, I always use singular, I must confess. Even I don't have license for magma, but I mean, for these kind of things, I don't believe it would change much, because we obtain solving time which are very, very short one.
Any other questions?
Yeah, I would like to ask you maybe a silly question, okay? So, but I'm trying to understand. So you have this one sigma, right? This one automorphism, and so I think that you know, if you said that if you can capture even in an intermediate state, then you can just come back to the initial state and you know and have a successful attack, right? So what did anybody try to use multiple automorphism sigma? I mean sigma 1, sigma 2, for example, and then to have some pattern.
You see, everything is possible, but it's natural to consider this way because we have some single parameter, which is discrete time, evolution of a vector over a discrete time. To have many parameters, so partial difference equation, would mean evolution over more, you know, more parameters. This is somehow unnatural. At least the easiest idea is this way. In fact, if you we started with some sets of equations for I mean real ciphers that were of this kind. For instance, trivium is given by means of these three equations. So since we had some, I mean, some experience with this difference equation of formal theory, etc., we immediately realized that we are dealing with such kind of object, and so it's a very natural that you have just ordinary difference equation instead of partial difference one. I don't know if I understand your question.
Yeah, you're completely right. I mean, that's my goal was to make it. I mean, like a you know, hell for attacker, right? So it will not be able to break it because even the difference structure is somehow complicated to even.
But you see, even with ordinary difference equation, 3 equation, 2 equation, may be extremely difficult. So it's enough. Of course, we can use the non-commutative structure. Why not? I'm for non-commutative cryptography. But you see, if you consider from this viewpoint, even a couple of quadratic difference, ordinary difference equation may provide an extremely difficult cipher to attack, etc. And consider also the fact that you want some, I mean, efficient encryption, decryption. Encryption, decryption should be efficient. Otherwise, you can, in mathematics, you can search for anything. You find plenty of difficult problems that that cannot be solved. Even theoretically, you can prove that are unsolvable by a Turing machine. But the problem is that you have to balance this security, so difficulty to attack, with some practical, efficiency for the encryption, decryption. So what I'm proposing, this different, not me, but also in practice, this system exists already. This, system of difference equation provides some, efficient encryption, decryption, and from the viewpoint of security of the algebraic attacks, they can be extremely difficult to attack. Algebraic or some other kind of attack. The main example is trivium. Trivium is 3 equations. It was developed in such a way to provoke people to analyze in this kind, by means of this kind of ideas. And the developer demonstrated that with 3 different equations, 3 quadratic equations in explicit form, they can define something which is up to now very difficult to attack. So it's not bad. Thanks. Very simple idea, very effective. Where does the Ri in the different system trivium? Why they choose this Ri 93, these numbers? This is again the design of the system. This Belgium designer decided to put these large numbers. I can explain why they are quite large, because the state is 288. It's about 300 bits. So the internal state is quite large to make difficult some algebraic attack, because you have to solve in the best, in the best way, you are reduced to solve over the initial variables, and the initial variables are 288, so 300 variables. A system with 300 variables to solve, with some, quite large degree, etc. But the key length is 80 bits, and the key length is 80 bits. So your attack, the complexity of your attacks should be bounded, is bounded by the brute force attack, which is 2 to the power 80 or 160 if you consider the initial vector. But you have to attack 288 variables. And so we tried ourselves, but we needed more than 80 variables to evaluate in order to have some Greber basis in a reasonable time. That's the point. So the designer of the trivium decided to have some quite large internal state, 300 bits, more or less. And this, it imposes some quite short key and initial weights and initial vector, which provides some bound for any attack. Any attack, any real attack should be less than brute force. This is typical, no?
So the crux of the algorithm in terms of security is simply based on the practical impossibility rather than theoretical. Is that right?
If you have something theoretical, would be better. But in practice, cryptanalysis is some amount of attempts. It's some amount of techniques trying to solve, to attack the. And so the minimal complexity up to now is the complex. It provides, a measure for the security of the system. For instance, this RSA, the security of RSA, this public key, private public key crypto system, the security was provided by the efficiency of the best factoring algorithms.
Yeah.
And during the 80s, 90s, people developed better and better algorithms to factorize large integers. But at some point, the research stabilized. So they decided that this RSA was safe. Okay. But at some point,
that's why
quantum computer appeared,
increasing the size. That's why they have to keep increasing the size. I mean, 256 is usually okay, but now it's 1,024 in the RSA.
Yes, but now there is this quantum computers, quantum techniques. So NIST, you know, this your National Institute for Standard, started a call for post-quantum cryptography. Yeah. But none of the proposed, now they are in the final stage, of this call for post-quantum cryptography. But none of this system is based on factorization. And why? Because there are some, you know, some algorithms over quantum system or quantum for quantum computing that can factorize in polynomial time. So at some point, something new, not in the mathematics, but in the hardware. I mean, in the
right.
Theoretical computer science, maybe, because I mean, this quantum computer up to now are just, I mean, small machine, but theoretically, and I mean, people really believe that in the next 20 years, this quantum computers will arrive. So NIST was involved in this call because they expect this.
So if the quantum computers are actually, you know, good enough, then the SAT problem would be solved in practice, right?
Yes, this is, I mean, RSA, yes, yeah. Because if
the
SAT, SAT solver.
Yeah.
Ah, you mean SAT solver? I don't know this, but I mean, you reduce this searching complexity by the square, no? So you reduce, if you are by, I know this, I mean, I don't remember now, but there are some, for quantum computers, are better search. And so better search will reduce complexity of brute force, and also to find by brute force the solution of this Boolean equation. And so, yes, probably.
Since you're using
SAT solver.
Yeah, since you're using Z2, so I mean, your problem is really an SAT problem, isn't it?
Yes. And in fact, in cryptography, people likes to use SAT solver for solving this system of polynomial equation over the field with two elements.
Right.
But our experience was, I mean, at least for this guess and determine strategy, where, I mean, all the systems are inconsistent. Symbolic computation performs better because we know this even by, I mean, the Gaussian elimination. To know by Gaussian elimination that a system is inconsistent comes from the fact that you obtain some equation 0 equal to 1. And for Greber basis, it's similar. Of course, the computation of Greber basis for inconsistent system may be very complicated, but generally it's better. Computing time is much better than SAT solver, at least in our experience. I mean, we tried with, but for inconsistent system, I mean, not for all system, because SAT solver are extremely optimized algorithms. So of course they are good. The people, I mean, electronic industry use a lot of the, we know this by these cryptographic problems.
So when you use Gromner basis in this algorithm, but do you use Gromner basis over the finite field of two elements, or over?
Yes, this I mean, this system are over zeta 2, over the the fit with two elements. In fact.
So the complexity of Grobner basis over Z2 should be very different from the complexity over integers.
Yes, of course, it's over the integers of the rational numbers may be very bad because of the
double exponential. Yeah, double exponential.
Yes, no, because of the length of the coefficients. There,
Right,
over
okay.
finite fields, of course, the coefficients are bounded, but very few is known, up to my knowledge, about complexity of Grobner basis. There are some worst case, which is very bad. Of course, it's unuseful. And there are some, I mean, complexity for regular sequences in terms of the complexity of this F5, F4, Fourier.
Right.
This, I mean, this is a Fourier variant of the Grobner basis.
But they are for integers. They are over integers, right?
No, they use also, no, because they are extremely interested in cryptography.
Oh, okay.
So they developed all of this over finite fields because they are quite much involved in this. I mean, in this NIST competition for post-quantum cryptography, there is one. One system for digital signature, which is made by these people, and it is based on polynomial maps. So security is provided in terms of Grobner basis. I mean, in terms of complexity of Grobner basis. And this, I mean, this system is already there in the final stage of this post-quantum cryptography. You can, it's called multivariate cryptography, which means to have cryptography in terms of polynomial maps, polynomial system, and security is provided by complexity of some methods, which are mainly, say, Grobner basis, this kind of things. And up to now, this digital signature made out of these polynomial maps over finite fields appears among the finalists of the competition. So it means that, I mean, polynomial system and so to say different system of ordinary equation are enough to provide in complexity and security.
Okay, thank you.
All right, so do we have any more questions? If not, let us thank Roberto again for an amazing talk.
My pleasure, my pleasure. Thank you.